Welcome to part 2 of our discussion on improper integrals. All right, so a second type of improper integral is in this form, integral from a to b f of x dx, where f is discontinuous at either a or b or both. And when I say discontinuous, we're not looking at integrals that go to infinity, but let's say, for example, we had the function 1 over x, and we had an integral going from 0 to 5. Well, you can't put 0 into x because of the discontinuity right there. And so we are discontinuous at a particular number. You cannot evaluate the function at that particular number. So that's what we're looking at. Instead of infinite bounds, we're looking at a discontinuous function. Similarly, an improper integral in the form of integral from a to b, f of x dx, where there exists a c, so some number on the interval from a to b, where f of x is discontinuous. Let's say, for example, you wanted to evaluate the integral from negative 2 to positive 2 of 1 over x. Well, you cannot evaluate 1 over x at x equals 0. 0 is on the interval between negative 2 and positive 2, so your function is discontinuous at a value somewhere in that interval. All right, so what we're going to do then is we're going to say the integral from a to b is equal to the limit as k, and again, this doesn't have to be a k, it can be anything we want, approaches c from the left of the integral from a to k, plus the limit as k approaches c from the right, from k to b. All right, so we're going to approach the point of discontinuity from the left and from the right. So let's take a look at this graph of f of x equals 1 over x. First thing we want to do is let's find the area bounded by f, the x and y axis, and x equals 1. So we're just going to take a look at finding the area of this part of the graph right here, first of all. All right, so let's do what we have done in the past, and we will say this is going to be the limit as x approaches infinity. I'm sorry, let me back up for a second. Let's just rewrite this as an integral first. So this would be the integral from 0 to 1 of 1 over x dx. Now, our integral is undefined at x equals 0 and cannot evaluate this. And so what we want to look at then is replacing 0 with some letter and treating this as a limit problem. All right, so we're going to rewrite this as the limit as, I'm going to use a, approaches 0. Now, we're on the interval from 0 to 1, so we're not really concerned with what happens to the left of 0. All we're looking at is approaching 0 from the right. So this would be limit as a approaches 0 from the right of the integral from a to 1 of 1 over x dx. All right, so we know the antiderivative of 1 over x is natural log, evaluated between a and 1. Now we substitute in, giving us the natural log of 1 minus the natural log of a. All right, so let's think about what we've got here now. The natural log of 1 is 0, so we can say this is equal to 0. and then the natural log of A as A approaches 0 from the right. All right, let's think about what the natural log graph looks like. So the natural log graph intersects the x-axis at 1 and looks like this right here. All right, so what we've got is a vertical asymptote for our graph. Now, as x approaches 0 from the right, this graph is going to approach negative infinity. So therefore, the limit as a approaches 0 from the right of the natural log of a means what's happening to our y values as a gets closer to 0. Well, this is approaching negative infinity. If this is approaching negative infinity, what that means is that this diverges. If you remember from the other video, diverges means that this does not approach a numerical value. This approaches negative infinity, so it diverges, does not approach a numerical value. So that means that this area cannot be calculated. It diverges. It does not approach a numerical value. All right, so then the second part of this question says, find the area bounded by f, the x-axis, and the lines x equals 1 and x equals negative 1. All right, well, what that would happen is we would break up this problem into the integral of this from negative 1 to 0 plus the integral from 0 to 1. Well, we know that this area diverges. If it diverges on any single part of your integral, then the entire problem or the entire integral diverges. So since this area or this integral diverges, this integral also will diverge. If any part diverges, the whole thing diverges. It's kind of like this right here. Even though this approaches 0, since this part diverges, this whole thing diverges. All right, so let's look at this problem here and write this out as the limit as a approaches infinity of the integral from 1 to a, and we're going to rewrite this as x to the negative 1/3 power dx, and the antiderivative will be x raised to the 2/3 over 2/3 evaluated between 1 and a. Okay, so this becomes the limit as a approaches infinity. Just going to simplify this a little bit. This will be 3a to the 2/3 power over 2, evaluated between 1 and a, which is equal to let me replace this real quick. This is still an x. Okay. All right, so now we plug in a, so you're going to have 3a to the 2/3 over 2 minus 3 times 1 to the 2/3, which is 1. So if you think about this, this is going to converge to 3/2, so that is a numerical value. Problem is right here, as a approaches infinity, well, because a is in the numerator, a will continue to get larger and larger and larger, which means this fraction is going to continue to get larger and larger, which means this part of our problem is going to diverge. This part does not approach a single numerical value. Now, if the a was in the denominator, then it would approach 0. But because a is getting larger and it's in the numerator, this will diverge. And because one part of this problem diverges, that means that the entire problem diverges. All right, so the question then becomes, if you have a integral that approaches infinity of 1 over x raised to some power, what is the power at which our problem converges versus diverges? Let's narrow this down to a rule that we can look at for our exponent to determine if this is going to approach a single numerical value or if this is going to diverge. We know that the function 1 over x approaches 0, but does it approach 0 fast enough so that we can converge to a numerical value? Or does it approach 0 too slowly and we keep adding values onto our function and we end up with a divergent problem? All right, so that's our question. What is our exponent at which this will converge versus diverge? Let's work this out. All right, so we're going to rewrite this as the integral from 1 to infinity of x to the negative n dx, where n is going to be a constant, not a variable, but n is a constant. So we will need to evaluate this. We're going to rewrite this as the limit as a approaches infinity of the integral from 1 to a of x to the negative n dx. Now, if we treat this as a u substitution problem, where u is negative n, then du, and if n is a constant, du will equal dx. Okay, so what that's going to give us then is the limit as a approaches infinity and the antiderivative of x to the u du will be x to the u plus 1 over u plus 1, evaluated between 1 and a. All right, so this now becomes the limit as a approaches infinity of a, and u was negative n, so we're going to put that back in, negative n plus 1 over negative n plus 1 minus, now we're going to plug 1 in. Now 1 raised to any power is 1 over negative n plus 1. All right, so I'm going to simplify or change things around a little bit so we can see what's going on here. I'm going to rewrite this as a raised to the negative n minus 1 over negative n plus 1. Now, what I can do with this part right here is, because this has a negative exponent, we're going to move this to our denominator. All right, so that's going to give us the limit as a approaches infinity of 1 over Now we need to think about, let's see what's happening here. Remember that n is a constant. So this fraction will end up being a constant. This fraction will converge. We're not worried about this part right here. A is what we're looking at, trying to figure out what's happening with A. Again, this part is a constant. You can think of this as a number 5 or 4 or whatever number this is, just a constant value. And so we're looking at the values of A getting larger and larger and larger. Now, we don't know what n is. If A stays in your denominator, then that means that as A approaches infinity, your denominator will approach infinity, which means this fraction will approach 0, and this will end up being a problem that converges to this fraction over here. Well, what if n is equal to 1? Well, if n is equal to 1, we got a problem, because you're going to have -1 plus 1, which is 0, in your denominator, and you can't divide by 0. Therefore, if n is 1, this problem will diverge. If n is a positive number, larger than 1, that means if n is larger than 1, that means your exponent is going to be a positive value, and that means A will stay in your denominator. And if A stays in your denominator, this fraction will approach 0. So repeat that. If n is larger than 1, the exponent will be positive, and as A gets bigger, your denominator gets bigger, which means this fraction approaches 0, and your problem will converge to this right here. Now, if n is 1, the problem diverges because you can't divide by 0. If n is less than 1, then your exponent will be negative. And if A has a negative exponent, A will then move to your numerator. And as A gets bigger, this fraction will diverge. It just keeps getting bigger and bigger and bigger. So we can come up to a conclusion then. Therefore, if n is greater than 1, then the limit, then the integral from 1 to infinity of 1 over x raised to the n will converge to a single value, and that value will be this over here. So again, if n is larger than 1, A stays in your denominator because your exponent's positive. And that answers our question here. Determine the values of n for which the integral is convergent. So if you have an integral of 1 over x to the second power, that will converge, and you can find out what it converges to. 1 over x to the third power, 1 over x to the fourth power, 1 over x to the fifth power, those will all converge to a single numerical value. If you have 1 over x to the 1/2 power, that is a number that is less than 1, which means 1 over x to the 1/2 power would diverge. That integral will only converge if n is greater than 1.